There is a persistent assumption in AI engineering. If an agent's plan isn't working, you just give it more time to think. You let it reflect, revise, and calculate a new path. But look at this chart plotting reflection iterations against accuracy on logic benchmarks like GSM 8K. Without an absolute ground truth, an oracle to guide it, the system does not improve. As the reflection cycles increase, accuracy steadily drops. This exposes an architectural paradox in agent design. Pouring more computational deliberation into a system does not automatically translate into a more accurate or safer outcome. I'm the bearded AI guy. On this channel, we break down the exact internal architectures of autonomous systems to understand why they actually succeed or fail. Today, we are analyzing research on metacognitive planning to dissect a specific structural failure. Autonomous systems fail when they have to decide how to decide. Infinite replanning loops are the silent killer of AI engineering. Early language models operated on static, linear prompt chains. You passed a text input and it printed an answer. But real-world environments are dynamic and require systems to constantly adapt to changing conditions. To establish a baseline for successful autonomy in chaotic environments, we have to look back to NASA's Remote Agent Project. In an October 1995 simulator test, the spacecraft's autonomous agent encountered a cascade of unexpected simulator errors. Instead of crashing, it repaired its plan on the fly and achieved its time-constrained objective. It survived because it utilized a closed-loop execution architecture: plan, execute, observe, and replan. The critical phase of this loop is anomaly detection. The agent actively monitors the environment, constantly checking if its predicted world state matches the live observations streaming in. When an observation contradicts the prediction, the agent faces an immediate meta-decision. It must choose whether to ignore the discrepancy, splice a localized patch into the existing plan, or scrap the entire objective and start over. Evaluating those choices is expensive. The internal deliberation itself consumes significant system compute, time, and attention. Adding anomaly detection transforms a simple task executor into a system burdened by a continuous metacognitive tax. Think of how a GPS works. If you encounter a sudden roadblock, the system recalculates a short detour from your current position. It doesn't wipe the route and map a new path starting all the way back from your driveway. In robotics, this approach is formalized as execution monitoring through discrepancy detection. This grid demonstrates the D Lite algorithm. The agent calculates an initial path, moving steadily until it visually confirms an unknown obstacle. Rather than discarding the map, it strictly updates cost-to-go values within the localized area, splicing an efficient patch to bypass the block and continue. The mechanism works because it relies entirely on a localized repair triggered by strict, observable evidence in the environment. Effective dynamic adaptation requires a surgical patch. Tearing down the entire plan and starting from scratch is computationally wasteful. This leads to the core trap of agent design. If a system spends all its allocated compute deciding what to do next, it executes nothing. The formal theory of rational meta-reasoning addresses this by splitting agent cognition into two distinct layers, an object level and a meta level. The object level contains the standard computational work. This is the agent actively generating steps and executing actions within the actual task domain. The meta level runs above it. It evaluates the internal calculation itself, determining exactly how much compute and time to allocate to the object level's planning process. There is a severe complexity problem here. Finding the optimal meta-level policy is mathematically intractable, with variance often mapping to p-space FARD complexity. This opens the door to the infinite regress failure mode. Without a strict stopping rule, the agent endlessly evaluates whether it should reason more about its own reasoning process. Unbound metacognition causes a system to thrash in internal cycles. It will exhaust its resources and time out long before it ever achieves the intended goal. We observe this in agent frameworks. On one extreme are highly reactive, step-by-step agents. On the other, rigid planners executing long task sequences. The reactive behavior maps to the react architecture. It operates on a continuous reason, act, and observe loop, designed for rapid micro-level corrections. Its structural vulnerability is oversensitivity. If the environmental observations are noisy or ambiguous, the agent triggers rapid micro-replanning spirals, constantly changing direction without making progress. The alternative plan and execute framework, a directed acyclic graph, feeds a linear task list into a replanning gate. It batches task execution before evaluating. If the trigger threshold is too low, minor errors cause it to scrap the entire downstream list, halting forward progress entirely. The visual architecture you choose explicitly predetermines how, when, and why your agent will fail under stress. There is a current trend in multi-agent engineering built on a flawed assumption that forcing a group of agents to debate will organically produce a superior plan. This exposes a flaw known as metacognitive mismatch. Raw planning effort simply does not correlate to increased decision quality. Recent data on multi-agent debate reveals what happens without a verifiable ground truth. Instead of correcting the group, stronger, accurate agents will actually conform to an incorrect peer consensus. The underlying mechanism is driven by agreement dynamics. Without a definitive anchor signal to evaluate against, the system mathematically amplifies the error rate round after round. This group failure showers the exact same root cause as single-agent reflection. If the feedback signal is weak, every iterative self-edit is just another opportunity for the model to drift away from the correct state. Unbounded reflection without absolute oracle labels does not refine a plan. It is literally toxic to the agent's overall accuracy. This leaves us with the final architectural question. How do engineers safely implement closed-loop planning in unpredictable, dynamic worlds? The uncomfortable engineering reality is that true autonomy requires hard-coding the system's ability to forcibly stop its own replanning process. You must establish a metacognitive budget. This means explicitly defining exactly which environmental discrepancies matter to the final objective and which ones must be ignored. You have to enforce rigid termination limits. There must be a strict computational cutoff where the system abandons evaluation and executes an action rather than endlessly editing itself. A plan is merely a hypothesis, and monitoring tests that hypothesis. But an endless reflection loop is a trap that demands immediate execution. If you want to keep reverse engineering the future of autonomy, make sure to subscribe to the Bearded AI Guy. Down in the comments, let me know what specific metacognitive limits and stopping rules you are hard-coding into your own agent frameworks right now. We will continue breaking down the human architect's blueprints in the next episode. I'll see you then.